think we stopped right here. Is that right? Yeah, we're getting ready to add, or actually multiply and divide right here. Now, let's review a little bit. I mean, we're going to do it again here in a second again, but what's the rule for multiplication and division? The least amount of sig figs. So if I multiply those top two numbers together without ever doing the calculation, how many sig figs should be in the answer? 3. Okay? How about the bottom one? 3. Okay? So try those, see what happens. So in this second one, are those two zeros significant?
Yes.
Why is that? What's the rule there? Right of the decimal place, zeros are significant. Left placeholders of the decimal point, they are left of the number, right, into the decimal place. But anything right of is significant. So anyway, 912 centimeters cubed and 3.9. Normally I do those on the board, but I thought these were straightforward enough. You guys can handle it on your own. Okay? So, all right. There's something else that you should know. Counting numbers are exact numbers. If I have 3 apples on the table, how many apples do I have? 3. And that number has as many significant figures as you need, right, to do a calculation. Exact numbers do. Or a count, right? Counted items such as number of students in a classroom and so on. All right? So just to let you know that numbers that are defined are not measurements such as the number of centimeters in a meter, 100. That is not 3 sig figs or 1 sig fig. That's as many as you need because it's a definition. Cool? You guys with me? All right, so we'll use exact numbers in these calculations. How about the radius of a circle is 13.7 centimeters? Calculate the diameter of the circle to the correct number of significant figures. So we have 13.7 centimeters is the radius. And so what's the formula? Diameter equals 2r, right? That's a nice way to put it, isn't it? And so if that's the case, this equals 2 times 13.7 centimeters. And so 27.4. Now, this only has 1 sig fig, so I would write this as 30. Or which one's correct?
27.4.
The 27.4, because this is what? It's in a definition, isn't it? And so it has as many significant figures as I need. And you have to be aware of that. Okay, so this is the correct one. I did it on purpose to make you guys think about it. Cool? Yeah. So 13.7. The measurement with the fewest digits is 13.7, so we would keep those 3. All right. How about find the result of each of the following calculations for the proper number of significant figures? And so now this has multiplication and or division and subtraction in the first one, and the second one has multiplication and addition. So wait a minute, are there some math rules that we have to follow right here? Yeah. Now, when I have something on top of a division line, does that mean I should do that before I do the division? Yeah, I think that is correct. Do I sometimes make a mistake on these? Yeah, because I don't. Yeah, it's been a long time since I've done math rules, right? I mean, I'm pretty good. What would I do if I really wanted to make that clear? I would put parentheses. If I had made this slide, I did not make this slide, I would have put parentheses around those top numbers, right? And so if you watch me, I'm going to very quickly go in and I'm going to put those in, and then that way there won't be a doubt whether. Cool. So, yeah. How you guys doing? What's 80.21 minus 79.93? I did not store that. Hang on, just let me find a marker and get back over here. And so 80.21 grams minus 79.93 grams divided by 65.22 grams. And oh, is it centimeters, not grams? Oh, my bad. Oh, wait a minute, that's kind of cool. You know what we've got here? You guys hear what I heard? There's a cricket right there somewhere. All right. Now, there's a movie. See if you guys can name it. Squirrel! Up and away, right? Never mind. Okay, 80 minus 79. What was this again? 0.28 grams divided by 65.22 centimeters. What did I just do that was really wrong? Is there zeros? How many sig figs are over here in the subtraction? There's 4, but it only goes, oh no, I didn't do anything wrong, did I? What happened to the other 2 sig figs? You go to the right on the decimal place to the place in addition and subtraction. So I went from 4 to 2 because of the subtraction. You guys with me? Yeah. All right, now I do my division. And that's going to equal what? 0. Let go in that trash can. No, maybe. 0.00429. I'm going to put a line right there. What do we need to do? We need to adjust that, don't we? Okay. So this is 0.0043 grams per centimeter cubed. Buddy, we're going to have a fight here. Nope, not there. Doesn't that drive anybody else nuts? Let's see how we did on that one. 0.0043 grams per centimeter. Yeah, we got that one. How about the next one? What are you going to do first? Multiply. And so we're going to take 92.12 milliliters times 0.912 grams per milliliter. That's going to give us grams per units. And then we're going to add plus 223.02 grams. All right, so what's the product of 92 times 0.91. 80 what? 84.20. 1, 2, 3, 4. 1, 2, 3. Oh, there's actually only 3 there, isn't there? But we're going to hold that because I think this is going to take care of it right here, right? Oh, 013? Oh, my bad. I heard that wrong. There's a cricket in my ear. Now, the way we have this set up, plus 223.02, where we're going to truncate it is right there. Do you guys see that? Okay. So, anyway, what's the answer to that? 0.03, and that is grams. Cool.
I have a question.
Yeah.
So when you multiply, would you only have, because 3 significant figures, would you only have 84.0?
You should hold all the numbers until the very end and round at the end in terms of that, right? I believe that is the case. Nope, I got that wrong. It should be 307.0, and so you're correct, aren't you?
So,
dang it.
So how do you know?
How do you know?
Yes, like
because you follow the rules.
Well,
so we did the multiplication, and we should have ended up with one shorter, and I left it.
So like, how do you know when to hold off at the end of it or do it and stuff?
Well, always in scientific measurement, we always do all the steps to the very end and then round at the very end.
Okay.
And so that was a mistake of mine. I violated the significant figure rule by trying to do the measurement rule. And does that make sense? Yeah, and so it's a combination of both of those. And so I messed up a step in that calculation. Cool?
Yeah.
Yeah. And so, do we sometimes make a mistake in it? And the answer is yes. Every real person does, because we're not perfect, right? And so, yeah, we do our best, and then we check our work. And when we graph it and those types of things, we try to make sure that we graph with the appropriate number of significant figures and that we've calculated those correctly. But you'll see it in the literature sometimes where someone will make that same mistake.
Okay.
And as an editor, if you're editing, you're supposed to try to catch those things and send it back to them. So anyway, logarithms. Anybody? Oh, you guys remember logs, right? Don't do that, okay? Everybody get their calculator out, okay? Everybody get their calculator out right now. I want you guys to do a function. We're going to do a function. Is that okay? I want you to put in the number 10. Type in the number 10. Okay, you guys ready? And then we're going to do a function, and we're going to do times 2. Okay? Everybody do 10 times 2. You done? That's just like doing a logarithm. No, it seriously is. All right? Log base 10 is a function. It's just like saying times 2. It does the exact same thing every time you use it. And then if you go backwards, the inverse of log, right, it's 10 to the power of. That's an inverse log function. Cool, you with me? Don't make them harder than what they are. Log does the exact same thing every time you use it. Takes, well, let's say the concentration of the hydrogen ion in solution, right? The concentration of hydrogen ion in solution when the solution is neutral is right around 10 to the minus 7 molar. Right? You guys with me? And if I take the negative log of 10 to the minus 7 molar, does anybody know what that gives me? Every time I do it. It equals 7. What's neutral pH? 7. When I take the negative log of 10 to the minus 7, what's the answer every single time? The calculation right here, which equals pH. Every time I do this calculation, negative log of 10 to the minus 7, what's the answer? 7. Every time I do 2 times 10, what's the answer? 2 times 10. It's 20 every time you do it. You with me? So don't make logs harder than what they are. We have a tendency to. It's a scary word, isn't it? Oh my God, it's a logarithm. You just manipulate them, okay? Just like you do an algebraic function. And so don't be afraid of them. They're useful. They make numbers like 10 to the minus 7 a whole number that even biologists can use to understand how acidic it is. What does it mean to be a pH of 2? Anybody? It's acidic. What about a pH of 10? Basic, right? Isn't that, now wait a minute. What's the pH of a solution of hydrogen ion that's 10 to the minus 10? It's basic because you just did the math in your head, you took the negative log, and what's that pH? 10. You guys catch that? It actually is easy once you learn how to use it. And useful. Okay, so just throwing it out there. Now, there are some rules. The number of digits after the decimal place, 3.5, you guys see that? After the decimal point of a log x should be equal to the number of significant figures of x, right? So 3.5 times 10 to the 5th power is 1 to the right of x. So if I'm looking at x, 3.5, how many significant figures? I'll say it right here in a second. How many sig figs? 3.5. 2. The answer should have 2 significant figures right of the decimal place. Do you see it? If it were 3.50, how many digits would be past the decimal place? There would be 3. It would be 5.540. You guys with me? The rule. All right. Now, the inverse log, if I'm looking up here, inverse log of x to the 10x, the number of significant figures in the answers equal the number of digits after the decimal place. So I have 3 after the decimal place, 10 to the negative 3.421 is 3.79 times 10 to the 4th. Okay, so it's the backwards direction. Cool? Yeah. So, is this one hard to remember? Yeah. Okay, it is. Why? How often do you guys do logarithms? Not often. You'll do them more in here. Cool, you'll get to practice them a little bit. You'll get to love them. All right. Why do we use significant figures? What are we trying to tell the reader? We related this to precision, didn't we? Right? Now, in reality, I think that the precision is reported with the error of the measurement. And so there's a plus or minus value, a tolerance for that measurement that can be reported with it. In my mind, that's truly the precision. That tells me how tight my pattern's going to be when I get to the true answer. Does that make sense? Yeah. And so anyway, the rules for significant digits in addition and subtractions are different from those in multiplication and division. And so significant digits and decimal place digits are not the same. And there is no necessary relationship between the two. And in general, calculators do not give the proper number of significant figures. You have to do that on your own. Okay? And all digits in the coefficient of a scientific notation are significant. And if I have a counting number, that one's not on here, right? If I have a counting number, how many significant figures does it have? As many as you need. Okay? If you have a definition, how many significant figures are there? As many as you need. Okay? So anyway, this is maybe my favorite part. I started on this earlier, and I will harp on this all semester, so you guys will get tired of me saying it. But if you aren't doing dimensional analysis, you're making a mistake. Okay? And every measurement should have units that go with it, and I report those, I should always write those units with it. It's just as important as the number. If I don't know what the number's measuring, then it has no value. Cool? All right. Always use full spellings or standard abbreviations for all units. Okay? Units can provide a clue to which operation, multiplication, or division should be performed in calculations. I think that the best way to do that is just to do it, right? To practice it. And so here we have, what are the total wages of a student who's paid $9 per hour for 30 hours a week? You guys can do this, right? 9 times 30 equals the amount of money, right? Cool? $270. But this is showing dimensional analysis. Now, did you do that one in your head? How many people did that in their head as soon as it went up? I said it out loud. I did. Okay? Did I cancel units in my head too? The answer is yes. Okay? I did the units at the same time I did the multiplication. Yeah. Now, if I'm doing this in a laboratory and I'm doing it in a laboratory notebook, should I put my thoughts down on paper? Yes. And should I put the units with it? Yes, absolutely. Okay? I can't encourage you more. This is just showing, writing down the quantity given, occasionally a conversion ratio, all right? This gave us in that $9 equals 1 hour of work, right? I divided both sides by 1 hour. That gave me the conversion factor of $9 per 1 hour. And so my hours canceled and I end up with $270. So we do this so much in chemistry, it's scary. All right, how about 5,445 minutes to hours? We need a conversion factor. How about it? What's our conversion factor from minutes to hours? 60 minutes. And I'm just going to say equals 1 hour. Can I do that? Because that's the way I would write it. If I'm trying to set up a calculation and I'm not sure, so 60 minutes equals 1 hour. Cool? And so that means that I want to convert minutes to hours. Where do I want the minutes to end up on if I'm trying to get rid of them? On the bottom, because the minutes in that number are on top, right? You guys with me? Now, I'm just talking about a division line, right? I'm not doing anything fancy, but I don't divide in my life, so I call it a multiplication line. That's a joke. Anybody else laugh at that at all besides me? Okay? So, but if I'm looking at this 5,445 minutes times 1 hour divided by 60. Now, did I use an abbreviation right there? Is this one acceptable? Yeah. So I hope it is. And we're getting rid of it anyway, so now we have the appropriate number. So what's 5,445 divided by 60? 90.75. And I have a question. Have I got the right number of significant figures? Is this a definition? The answer is yes. And so that means I should have kept the number of sig figs from my original number. Cool? All right, so we just did that very quickly. We have the minutes, we have the definition of an hour, and we made our conversion. Cool? Fun, huh? How about how many meters are in 5.2 kilometers? How many meters are in 5.2 kilometers? 5.2 kilometers, the definition that we need are 1,000 meters equals 1 kilometer, right? So which is going to go on bottom and which is going to go on top? I need kilometers gotten rid of, so times 1,000 meters divided by kilometers. You guys ask me, how do I know how to set up the calculation? How do I know? I know the definition, and then I rearrange it to cancel the unit that I want to get rid of. That's better than a formula, isn't it? Because then I can do any calculation. I can take a word problem and set it up in this fashion based on what I'm given. Okay? So anyway, well, I forgot 2 zeros up there, didn't I? 0, 0, and so this equals 5,200 meters. Right? You guys with me? Check our units. You go back and check, make sure you got it set up right, and she did cancel. If I set it up upside down, then I would have ended up with kilometers squared divided by meters. And that's not the unit I'm looking for, is it? So I can check. What about the next one? 5.22 micrometer. 5.200 micrometer. Um, 10 to the minus 6 meters equals 1 micrometer. That's the correct definition? Yeah. So that's the one I have stored in my brain. That's why I wrote it that way. Cool? Could you have written it as 1 meter equals 1 million micrometers? Yeah. Okay? So I could have written it that way too. However you store it in your brain. But then I would multiply this times 10 to the minus 6 divided by 1 micrometer. And look how easy this is. 5.200 times 10 to the minus 6 meters. I like it when math problems work like that. All right, so here's 5.2 times 10 to the third. Oh yeah, wait a minute. Why did they do that up there on the board? Instead of leaving it like this. How many sig figs are supposed to be in this answer? 4. How many do we have right here without any further definition? 2. So we rewrite this as 5.2 times 0. God, that thing's driving me nuts. Cool? All right. And I automatically did that in the next one, right? 5.200 times 10 to the minus 6 because that made the math easy. I just wrote that on to the end of it. Cool? All right, so how about this one? Multiple conversion factors. Calculate the number of seconds in 5.175 hours. I'm going to tell you this right now. I would only use one conversion factor right here because I know it, it's automatic. All right, but I want you to use 2 because they're using 2. And I'll do it with 1. Cool? That means we need another definition on the board. What definition are we looking for right now? 60 seconds. Can I use SEC? And to 1 min. Alright, so now I have all the definitions that I need on the board. So you guys can do that calculation. I'll let you do it. Is this really any harder? And I have a question. Can you do it as 2 calculations? Or just 1 or both? A, B, or C? A, 2 calculations. B, 1 calculation. Or C, you can do it either way. C, you can do it either way. So this is the way I was asking you to do this. Let's check to see if I have the setup correct. I have hours canceling, right? I have minutes canceling, and my answer's in seconds, isn't it? You with me? And so this is 18,630 seconds, right? I know this conversion. It's one of those things that's randomly in your brain. And so I would have, if I had read that question, I would have automatically done 3,600 seconds per hour. What's 60 times 60? 3,600. And so, cool, you guys with me? For some reason, 6 times 6 may have been the first, big number when I was in elementary. I remember because I just really thought it was cool. It was the 6 times 6 was 36, half of 6, and the number itself. I don't know, it's weird, I know. Okay, you're gonna find I give those things up every once in a while. Or like multiples of 6, 3, 6, and 9. 2s were too easy. Cool? All right. Definitions, here's doing it one step at a time from hours to minutes. And then to take that and from minutes to seconds. So we can do it in that way, or we can do it as one calculation with multiple conversions in it. Doesn't matter either way, it's fine. When you guys are doing your calculations, I don't care whether you do them all in one calculation or in multiple. I have a tendency to do them in one. Why is that? It's quicker. To me, it's more efficient. Now, sometimes I even have to go backwards the other direction. There's an intermediate that I might need, but it's still, I go to the end usually to start with. It's just me. I don't ask you to do that. Okay, I'm just telling you that's what I do. All right. Oh man, if you had $1 billion, right, and you spend $1,000 a day, right? How long would it take you to spend it? All right. How many years would it take you to spend $1 billion at $1,000 a day? There's 2 conversion factors in that. What do you need? What are the conversion factors? You see them? $365 days equal 1 year, right? Was there another conversion factor in that? $1 billion, excuse me. That's a lot of zeros. It's like 9 zeros. Right? Times, let's do it this way because I like it better. Dollars, right? $1 billion times 1,000 dollars per day. Now wait a minute, what did I do wrong there? I've got to divide it. Now I'm doing everything by multiplication, so this is the way I fix it. I just put a 1 over. Okay, you guys see that? Because I wrote the units out and I got them upside down. Now what happens to the day, which is on the bottom down here? Right, you with me? And so then times what? Times 1 year divided by 365 days. And so now my days cancel, my dollars cancel, and I have the number of years. Now, is this gonna be a big number or a little number? Big. All right, 2,740 years. So now, that means that if we spend $10,000 per day, which would be adding 1 0, you with me? We would be at 274 years, right? And then that means if we go to $100,000 per day, that would be 27.4. I think I could do that for 27.4 more years. $100,000 a day. Can you just imagine you could just go around and give that away every day? Wouldn't that be fun? Just to walk into a charity or a church or a bank and pay off like 10 people's houses? The thought, isn't it? So, what do you do with $1 billion? Right? You could try to make another billion like some of those billionaires. Or me, it wouldn't last that long. Actually, I would put it on in investments, and then I would just take the profit and give away the millions of dollars per year that I would make out of that. Put it in a foundation, and then it could go on forever, right? Scholarships for students here at CHE114. Pay tuition. Boy, no, that's already covered. To pay room and board. So all students at CHE114 get the room and board paid. If I get $1 billion, I'll do that. How's that? You bet. All right. So job A pays $500 per week, where job B pays $11.25 per hour. Both are 40 hours per week. Which job pays more? This is the comparison, right? Two ways to go. You can either calculate the $500 to hourly wage, or you could take the other one and multiply it out to find how much you would make in a week to see which one makes more, right? Which one do you think I would do? Huh? I would take the 40 times 11.25 because I don't like to divide. Still funny. $40 hours times 11.25 dollars per hour, and this would give me the dollars per week because it's a 40-hour week, wouldn't it? Oh, so needed one more conversion, right? 1 week is equal to 40 hours, right? I mean, that's what we're assuming. Is that correct? Yeah. So, and the other one is 500 per week. So now I've got week is my unit, and then we got the number 450.
50,
Oh, 450 dollars per week. I got this upside down, didn't I? Well, wait a minute. That's where I messed up. I added the conversion factors. Does that ever happen? That's ugly. Did I know it was wrong when I got there? What I did was I started doing units, and my units didn't work out. Did you catch that? And I was like, ooh, what did I do wrong? And so that's what it was, 40 hours per week at $11.25 per hour, and then the units would be dollars per week. So there, I didn't mess that up. How much is it again? 413. So yeah, that's exactly what I'm talking about. Why do we use units? To correct yourself when you make a dumb mistake. Yeah. All right. 500 times 1 week per 40 hours is $12.50 an hour, or which is more than $11.25, Or we could look at it from this perspective, $413 per week. Yeah, which one would you guys do? I don't know, it wouldn't matter. All right. Oh, here's the other way. One way or the other. All right, so what's amazing is that Taco Bell is now paying more than that in Branson, Missouri.
McDonald's pays more than that too, and you get a bonus.
And you get a bonus for signing up?
Yep.
Wow, that's amazing.
Not that I work
And what about the one in Hollister? Are they the same?
there. And Menards will give you a bonus too. And if you work in the yard, you get an extra $1 an hour.
Hey, you go to Hobby Lobby, we're paying 17 an hour.
Wow. Cox Hospital just went to 15 an hour is their minimum pay scale too. So as a aide or a housekeeping or door person, then you'll make 15 an hour too. Because they can't hire anybody. Do what?
Everything's gonna get more expensive.
Ultimately, yeah, everything's gonna be more expensive, yeah. So, yeah, it's called inflation. Things go up and food's already gone up. I mean, people who are making minimum wage don't eat as well as they used to. Okay? Literally. So we're just trying to balance that. Yeah, things will go up with time. They always do. Guys, I paid 25 cents a gallon for gas. Right? Hey, I mean, that was, to get a gallon, it was 10 cents, a nickel a soda pop bottle, right? And to get a gallon of gas for my go-kart, right, I would walk down to the gas station with my gas can in the bag, and I would pick up soda pop bottles along the road and try to get enough. If I found extras, I had a tree stash where I'd put them behind the tree. And I'd go get my gallon of gas, and then I would take it back to the house so I could drive my go-kart.
And now on the West Coast, it's over $4 a gallon.
So I bought 3 here, so anyway. All right, dimensional analysis units may be canceled, all right? Like variables in algebra, placing units so they cancel to get the desired units will help you to correct a calculation. Some conversion factors are constant, such as the number of cents in a dollar. Others are variables, such as the number of miles traveled by car per hour. And so those must be given in the problem. You know, before we had GPS and you were on a road trip, and you'd have to take a map and measure the miles that you were going to go, right? Pick your route. And then to estimate how long it would get there, you actually had to do math. Did you know that? Now you just click that button on the GPS, I want to go to Akron, Ohio, and it will take the shortest route, calculate how long it gets to get there. We used to do math to find those things. Place you'd never been before. Isn't that crazy? Estimate your speed. You go about 60 miles an hour on 4-lane. Average that maybe 70. For a while, they dropped the speed limit to 55 to conserve gas in the 70s. That was an awful world. Okay? You ever tried to drive 55? Yes, everywhere. Yeah, they went from 70 even on 2-lane roads, like the highways, the 2-lane highways. They dropped it all the way to 55 on everything. Oh yeah, trying to conserve gas. Don't miss that. Calculate density, volume, or mass when 2 of the free values are given, and then you can identify substances using density. What is density? Mass over unit volume. Simple as that. They can read all the definitions up here. If I have an object that is less dense than what it's floating in, or than what it's in, then it will float, right? If I have a helium balloon, it's less dense than the air around it, and so it will float up. Do you guys agree with that statement? If I have a ship and I set it on water, it floats, doesn't it? Wait a minute. If I take an iron ball and drop it in water, then how does it float? It doesn't, but if I take an iron ship and I do, how does it float? Because it has air in it, it has more space that's air than iron, and so the density of the entire object is much less than the water, and so it sets on top of it. Cool? Yeah, until I fill it up with water, which is a bad thing, right? So, just throwing that out there. we'll use this. This is the last section in this chapter. Actually, that's not true. There's a temperature section following this one. But mass over unit volume. And so it's easier to look at it from an experimental standpoint. If I have an object A and B, and they have the same volume, but A has a greater mass, which is denser, A or B? A is it has more mass per unit volume. You guys with me? And so that's showing that on the balance up there. And then objects C and D have the same mass, but C is larger, which is more dense. D is more dense, right? So that's just an idea. Object A has more mass per unit volume than object D. So that means the others are less dense. So that's just that idea. Now, we can use this to identify, if I have a small piece of aluminum, does it have the same density per unit volume as a large piece of aluminum? It will weigh less, but it has the same density. So I can use it to identify that substance. And in fact, now I will tell you, and in fact, I'll show you why it's such a bad idea. Now, many boats are made out of aluminum. Okay, you guys are aware of that, right? Why do they use aluminum? It's less dense, and so the boat is more buoyant. Would you guys agree with that statement? Yeah. And so, now, battleships are generally made out of, and shipping ships out of steel, right? And in fact, they make alloys of titanium and so on. I mean, we always talk about the Titanic, which was a titanium hull, which actually was too rigid, right? And so it fractured when it hit the iceberg, and when it did, it sank like a ship. So it went to the bottom. But now, there was actually a proposal made to the United States government to build magnesium battleships. All right? Because they would be very hard, because magnesium is very hard, much less dense, so they would be extraordinarily fast, right? Why is that a bad idea? I'll show you on Wednesday. Okay?
Sorry, clickers?